So people have probably seen this picture before, which I think kind of tries to summarise what's going on here. There's an occultation, if you like, of how visible geometry works, right? And they're replacing it with this idea that we're living on a space ball. Yeah, total nonsense. Yeah. So I'll just set a bit of context there. This might be a bit of repetition, but I think it just makes sense to go quite a few slides that.
Sorry, Gav, see, just before we go into this, because I'm forgetting, in case there's anybody new here, what's established so far is that, there's two different geometries at play. There's a geometry of the space that we move around in, and then it's how that appears to us through our vision. And that vision has a separate geometry to what the actual space is. Right? So this is where we're talking here about the geometry of vision and how things appear to us in the visible field. And that's it. It's just a quick one for anybody that may be wondering what the fuck we're talking about, or the relevance of this.
Yeah. So the picture I've got up on the screen shows on the left-hand side our tangible world, the world we move in about in. There's a little figure there, and we've got all kinds of objects in our daily life, right? Cylinders, cubes, pyramids, balls, blocks, you name it, right? And that's the world we live in, the physical substances, objects, stuff, right? And that 3D world is where we move in. And as you quite rightly said there, there's another visual world, which is different from the tangible world. And that differentiation, or the ability to attend to that difference, to discern it properly, is something that's not easy to do, because we all have eyes and we use them every day. So it's not always obvious to us that there's something different at play.
Yeah.
We just tend to think about the physical objects all the time.
Yeah.
But anybody can see for themselves that objects change shape, depending on your position, the angle at which you're looking at it. So a table doesn't look like a square table from a side view. Or from an oblique view, it looks like a trapeze or something completely different, right? So, and the ability to differentiate these two things is really important in understanding how the lie is working. Yeah. So your visual space or your visual perception has everything to do with spherical geometry, which is what we're talking about here. I'm not going to go into detail on the other things on this picture, but so if you like, there's two different geometries at play here. There's the geometry of the physical space down at the bottom, which is everything to do with substance, construction, storage, manufacturing, transport, engineering, mechanics, all the things that we do in our daily life and people build and construct with, right? Parallels, levels, plumbs, it's all Euclidean geometry. And it's all part, if you like, of natural science, right? And part of our human nature, our lived life, right? Our physical reality. And these things, as far as I'm concerned, are all objective truths, yeah? I mean, anybody can pick up a brick, anybody can play with water. So all these things is something that, they just are there, right? Yeah. And we can all experience them. We don't need to reason about why they're there. We can speculate why they're there and who built them and who made them and all that kind of stuff. But at the end of the day, human life and the world in which we live in, is, and we can observe it. We can, discover how the laws are, how they operate, but we don't really have a clue who made them and what's behind it all, right? So, and the top half of this is the geometry of visible space, which, as far as I'm concerned, has been used in things like astronomy, the celestial sphere. It's used in navigation, it's used in dialing, which is like sundials and telling the time and clocks. It's used in surveying, geodesy. So everywhere vision is used to calculate something, or calculate often based on assumptions, then it's the geometry of vision that plays a role. Yeah. And there's different kinds of visual spaces. Spherical is something that people don't realize that's how their vision works. And a lot of that is then changed using language, and mathematics is a language, to give us all kinds of stories about space balls and globes and beliefs and cosmologies. And as far as I'm concerned, all these things are subjective, Dale, right? There's certain truths to certain mathematics. I'm not denying that, right? Like Euclidean geometry, the very fact that it's used so successfully tells us that.
Yeah.
But at the same time, all these cosmologies and space balls and infinite universes, these are all things just based on mathematical physics, yeah? And there's absolutely no proof for any of the stories they're telling us, yeah? So, again, this is the example of a daily life. There's a picture out of my, general world here at the top. I know that fence is really, the square sections, so to speak, yeah, or oblong rectangular sections, and that the slats of wood, they're all the same, and that the barn here on the left-hand side is also, rectangular. But the way the whole stuff looks to the eye down at the bottom, that's what it really looks like. Well, that's what we're seeing, right? We just don't necessarily, we're not aware of it, Dale, because just while we're looking at that building, we're thinking of a big rectangular barn or a piece of wood that's obviously rectangular.
Yeah.
But at the end of the day, what's being registered to your eye, what's actually on your retina, are these shapes, not the shapes of the real world. Yeah.
And it's one of these things that people don't. Again, it's the same as what I was just talking about before. People don't realise these things until it's highlighted. It's just, again, things that you're born, you live your life, you take things for granted, and people are not paying attention at the level that we're talking about right now. So
exactly.
Yeah.
Yeah, and I think that's why it's easy for people to tell narratives, because if most of the population or the majority of the population doesn't discern between physical and visual geometry, then there's obviously a lot of scope there to tell a lot of lies of optical phenomena.
Well, every con relies on the participants' ignorance. So it's just the same here, just as you say. If you don't comprehend it, you're not paying attention to it. It can be used against you.
That's right, and they've certainly done one on us this time. So, I'm just going to skip over this one and go straight to what I think is maybe a pivotal piece of knowledge that will help people understand how this trick is being played, if you like. So here's a definition of a nautical mile from a mathematical textbook, yeah? Mm-hmm. And a nautical mile is defined as the length of the arc of a great circle which subtends an angle of 1 minute at the center of the Earth. So you're supposed to believe that the Earth is a big solid ball, yeah, and it has a center. And a nautical mile, as seen here on the right-hand side in an orthographic view, is then the length of this arc here. So this very small arc, it's the length of that when the angle at the center is exactly 1 minute. And it's seen here, 1 minute, there's 60 minutes in 1 degree. We usually know that a circle has 360 degrees. And each degree has 60 minutes, which basically makes 21,600 minutes in a circle, yeah? And one of these minutes is then the arc length from the center of the Earth is what they define to be a nautical mile. So that's one definition of a nautical mile. I'm going to produce another one here, which is different. This is a practical definition of a nautical mile, and also the way people navigate on water. So the way it's defined is that a nautical mile is the length or the distance that you need to travel to see a change in altitude of 1 minute of something. Yeah. So altitude is basically the visible position of, let's say, a lighthouse. So here's a lighthouse on the left-hand side. There's me at this position, and you, Dale, slightly closer to the lighthouse. Now we are going to see that light in a different visible position from each other. Yeah. And if we wanted to calculate the distance between us, if you see that light 1 minute dropped in your visible vision than me, then we know that we're 1 nautical mile apart. Yeah. And that's the way people navigate. Normally they don't use lighthouses, they'll use the sun or the moon. They'll take a sighting, and that way they can to travel. So that's the whole concept of the celestial sphere, which I'm not going to get into in too much detail. But the important thing is here, if you distance yourself from an object, in this case a light tower, and the thing drops 1 minute in your visible place, or its visible position in your field of view, then you've traveled 1 nautical mile. And that's the way people navigate all around the world, Dale.
Yeah.
Today.
Yeah.
And you'll see that these two different definitions are completely different, right? So this one is relying on a mathematical model telling us that we're on a ball and defining what a nautical mile is based on the idea that, the Earth is a radius and there's a ball. In fact, they say that a nautical mile, the radius of the Earth is 3,438 nautical miles. So that's a mathematical concept. And this one is a practical concept. You're on water, we know water's level, and if you move backwards from a luminary or from a light in 1 nautical mile, then it will change its visible position. It will basically drop in your visual field 1 minute, 1 arc minute. So given those two different definitions, the question that really comes up is, which one's real? This is the one they all want us to believe, right? And this is the reality of the situation. Yeah. And here's a little bit of text, just for people who want to follow along. And a nautical mile is the length of the arc of a great circle, which subtends an angle of 1 minute. And it also introduces the concept of a radian, which I think I'd like to leave to another day. So I'm just going to use this concept of a radian without completely defining it, and we'll come back to that.
Yep.
But what happens here is that the number of minutes in a radian is equal to the number of nautical miles in the radius of the Earth. And what pops out basically is this number 3438.
Yeah.
So that's what they actually tell us the radius of our space ball is in nautical miles. You'll hear different numbers depending on whether they use statute miles or kilometers or whatever. But as far as nautical miles are going, that is apparently the radius of the Earth, 3438. And as I say, there's two different, if you like, definitions. There's the mathematical model, and then there's the practical model. So bearing that in mind, and this number 3438, I'm going to jump differently to a different subject, and then we'll come back to it. The different subject I'm going to talk about is visual acuity and the visual angle. So this diagram is taken from a book about 20/20 vision. In fact, it's a book, Dale, that in fact, I think I've got it here. Just let me bring it up. Yeah, I have. This is a book written by an American physics department, and it's to do with what size of letters do you need on an eye chart, right?
Yeah.
So that they are visible. So when you're doing, your eye test, you usually got one of these eye charts with numbers on it, and you stand 15 feet away from it, and you're supposed to, see if you can read all the letters, and they'll tell you how good or how bad your vision is, right? And this document is talking about the size of the letters that you need to draw and the gaps in between them, so that you can draw signs that are clearly visible, and it depends on the distance and the observer's visual acuity. So it's trying to basically measure visual acuity. Yeah. And if I go back to the PowerPoint, then one of the important topics in here is the fact that your retina is a curved surface. Yeah. And if I'm an eye looking at a chart on the wall, then the question that is asked is, or the definition of a visual angle is this angle here that basically encompasses the whole object. So the object starts at A, it finishes at B. You can think of it as one of these eye charts hanging on the wall. You're at a distance D from it, which might be 15 feet, let's just say, to take an example. And then the question is, what is the angle subtended at the eye from that object, AB? Yeah?
Yeah.
And you can work out that angle. On the next slide, I'll just show how it's done. The visual angle is basically the height of the object, or the width of the object if you were looking at something horizontally, but let's assume it's still an eye chart. It's the height of the object divided by the distance from it. Gives you the visual angle in radians. Yeah?
Yeah.
And again, I'm using this concept of radians without specifically defining it, but the radians is a way of intrinsically measuring based on the radius of a circle. So instead of using degrees and minutes, you basically use the radius of the circle to measure how far you are around it. So if you like, it's something different to degrees and minutes, and it's called radians. Yeah.
Yeah.
So this is clear. The visual angle subtended at your eye depends on the size of the object and the distance you are from it. Yeah. And if you want to convert from radians to degrees, there's a way to do that, which I'll just follow the bouncing ball for those who want to follow along. It basically turns out to be the visual angle in minutes is 3438 times the size of the object divided by the viewing distance. Yeah?
Yeah.
So this magic number 3438 pops up again in visual acuity. Visual acuity being how far can I actually see before things are no longer discernible to me? So what's the limits of my vision, basically? And this formula, just to give you everybody an example, would mean that if you had a coin of 1 inch of diameter and you put it at 3,438 inches from you, which is 286 feet or 95 yards or 87 meters, right? Then the visual angle of that coin will be 1 minute. And basically at 1 minute, Dale, that's where your visual discernment stops.
Yeah.
So some people can go a bit lower, right? Depends on age and lighting and, various conditions. So this isn't exact, but basically if something is less than 1 arc minute, then you can't see it anymore. And anybody can try this, Yeah. Take a coin, put it at 87 meters and see if you can see it still. Yeah.
Yeah.
Or take a dartboard, that could be 1 meter. You would then have to go back 3,438 meters and you wouldn't see it. So it doesn't really, it doesn't depend on the size of the object. The formula is there all the time. And this magic number 3438 is there in the whole topic around visual acuity. And it just happens to be the number of nautical miles in the so-called radius of the space ball.
Yeah.
So people could think this could be a coincidence. I don't think so, right? That basically this ratio of 3438 is where, if you like, the imaginary curve is supposed to happen, Dale. Yeah. Do you know what I mean? Just beyond our limit of vision, is where the curve starts, yeah.
Well, you see this in horizon images of ships apparently disappearing. And it's always the same. You ask the question, well, why does it appear to be a ramping up, and then at the point of the horizon it dips away? So as you say, this is the point at where they're saying that the curve is. That's when you're witnessing the curve of the Earth.
Exactly. Yep. Yeah, so this visual angle, the size of the object and the viewing distance. You've heard the old story about the moon is apparently, a lot smaller than the sun. They just look the same size because one's so far away.
Yeah.
So if you're obfuscating angles, or you're using angles in this concept of radians to measure things in astronomy and celestial sphere, then you can tell lots of stories about the size of the object and the viewing distance to make it fit, Dale.
Yep.
Yeah. Whereas if you're standing in front of an eye chart, it's 15 feet, yeah, and that it's 5 foot tall or whatever how tall they are, I don't know, right?
Yeah.
So getting back to the fact that we can walk to the chart, right? We can measure its dimensions using a ruler. We can pace the distance, yeah. So it's all right to use it in that respect and to talk about visual acuity, but it's very easy for them to use the concept of radians and talk a lot of shite about the size of objects in the viewing distance, Dale. Yeah? So if I go back to the geometry of visible space and the geometry of physical space, making sure that you understand that difference is absolutely imperative, right? And that they can get away with using it in astronomy and navigation only because they're actually using visible space to do their calculations, the geometry of vision, rather than the geometry of any real space ball, Dale.
Yeah.
And the concept of radians plays a big part in that.
Which again it's backed up by the very fact that they don't have a direct measure, as we were saying at the very beginning of this. There is no direct, tangible measure of the curve of the Earth.
No, absolutely none.